11.3 Matrices and Row Operations. Southwestern College, Professor Maria Olivas. Matrices and Row Operations. Objectives: define a matrix, solve systems of equations using matrices, and solve applications using matrices. 1. Definition of matrices. A matrix is a rectangular array of numbers. It is described in terms of its number of rows and columns. The order of a matrix is equal to the size of the matrix, which is also equal to the dimensions of the matrix. In order to determine the order of a matrix, you need to know the number of rows and the number of columns. And it needs to be stated in that order. Number of rows, number of columns. Number of rows has to go first. So now I'm going to write down here, order is equal to m by n, where m is going to represent the number of rows in the matrix, and n is going to represent the number of columns. I'm going to point arrows at m and n. The arrow pointing at m, I'm going to write down the word rows after that. And I'm going to point an arrow towards n, and I'm going to write down the word columns after that arrow. Examples. I'm going to go ahead and make a chart here. I'm going to make a chart that's a 2 rows and 3 columns chart. In the first column, I'm going to write at the very top 3 by 1 matrix. And in the space below that of this chart, I'm going to actually give an example of a 3 by 1 matrix. So I'm going to draw brackets on the sides of the matrix. And within the brackets, I wrote down one column that has the elements 1, 3, and 5. Row 1 is represented with the element 1. Row 2 has element 3 in it, and row 3 has element 5. We call the expressions or numbers within a matrix the elements or the entries of the matrix. Besides labeling the rows as row 1, row 2, and row 3, I am going to also write column 1 at the very bottom, pointing upwards towards where the number 5 is at, but it's representing the entire vertical column there. Rows go across from left to right, and columns go up and down. For the second column here of my chart that I drew, I'm going to write a 2 by 3 matrix at the top. And I'm going to give an example of a 2 by 3 matrix beneath that in the second row of that second column. As I'm listing the rows, I'm going to go from left to right. In row 1 of my matrix, we're going to have the elements 7, 5, 9. And in row 2, we're going to have the elements 0, 4, and 6. On the left-hand side, I'm going to write row 1 and row 2 pointing towards each of its corresponding rows. In column 1, we have 7, 0, and I'm going to go from top down as I'm listing the columns. So in column 1, we have elements 7, 0. In column 2, we have elements 5, 4. In column 3, we have elements 9, 6. In the very last part of my chart, the last column, I'm going to write at the top 3 by 3 matrix, and beneath that I'm going to give an example of a 3 by 3 matrix. In row 1 of this matrix, we have elements 1, 2, 3. In row 2, we have elements 4, 5, 6. In row 3, we have elements 7, 8, 9. So all of those elements, I've listed them off from left to right. I'm going to go ahead and just lasso this matrix and where I wrote row 1 for this matrix, and I'm just going to move it slightly more to the right. So I'm labeling row 2 with an arrow pointing at it and row 3 with an arrow pointing at it. Now I'm going to label column 1 with an arrow pointing up towards it. I'm labeling the columns at the bottom. Column 2 and with an arrow pointing up towards column 2, and then column 3 with an arrow pointing up towards column 3. The elements in column 1 from top down are 1, 4, 7. In column 2, we have 2, 5, 8. And in column 3, we have 3, 6, 9. So I've already stated that the order is the size of the matrix, and it's given as row by column. I'm going to erase where I wrote the order of the matrix is equal to m by n at the top. And in that area, I'm going to go ahead and I'm going to write the numbers symbols or expressions in the matrix are called entries or elements. I'm going to underline the word entries and elements. I'm going to use our 3x1 matrix as an example. I'm going to highlight the 3 entries or elements that we have in matrix 1 with my yellow highlighter, and I'm also going to circle them in red with an arrow pointed up towards them. And I'm going to say this matrix has 3 entries. We can take data that might be organized in a table and instead display the data in a matrix. Example 1. The table shows the number of TVs of different models sold last month at 3 different store locations. Here you see a table. This table has 4 rows and 4 columns. Underneath the first column, you see the heading of store, and then you see the La Mesa store, the National City store, the La Jolla store. And then for the next 3 columns, you see in the heading Model A, Model B, Model C. And it states the number that is sold for each of the stores. In the La Mesa store, there were 206 Model A TVs sold. So I'm just going to go ahead and list off the numbers from left to right for the La Mesa store. So in the La Mesa store, from left to right for Model A, B, and C, respectively, that's going to be 206, 180, 150. Then for the National City store, it's going to be 185, 201, 180. The La Jolla store, it's going to be 140, 160, 250. A. Express this data in matrix form. So I'm going to create a 3x3 matrix. In the first row, from left to right, we're going to have 206, 180, 150. In the second row, from left to right, we're going to have 185, 201, 180. In the third row, from left to right, we're going to have 140, 160, 250. This has 3 rows, and I'm writing the word 3 rows here on the left-hand side of the matrix, with arrows pointing to each of the rows, and then I'm labeling those rows as 1, 2, and 3. And if we look at the number of columns here, we see that this has 3 columns. I'm writing the number 3 and then the word columns right after that underneath the matrix, and I'm pointing arrows at each of the 3 columns and labeling them with 1, 2, and 3. For part B, it says, what are the dimensions of the matrix? The dimensions of this matrix is going to be 3x3, and I'm going to box that in. C. What is entry A23 and what does it represent? So A23 does represent one of the entries in the matrix. The first number in the subscript is a 2. That's going to represent that it's going to be in row 2. The second number in the subscript is a 3. That's going to represent that it's in column number 3. I'm going to go ahead and write next to our matrix the form of a 3x3 matrix where each one of the elements is labeled in this order, where we have element A11 in the first row, first column. You would have in the first row from left to right, element A11, element A12, element A13. In the second row from left to right, you would have element A21, element A22, element A23. In the third row from left to right, you would have element A31, element A32, and then element A33. So then that means for part C, where it says what is entry A23 and what does it represent, we are going to be looking at our matrix in row 2 under column 3. And if we look there, we're going to see that the number 180 is going to be in that spot. We could also compare the 2 matrices that I just wrote down here. If we look for the corresponding position to A23, where I have labeled it in my matrix, in comparison to the matrix that I wrote with all the data in it, you would see that these 2 elements are positioned in exactly the same spot. So entry A2, 3 or entry A23 is going to be equal to 180. And I'm going to go ahead and box that answer in. The second part to this question is, what does it represent? In this problem, this element represents the number of Model C TVs sold last month at the National City Store. Since row 2 represents the number of TVs sold at the National City Store, and column 3 represents the number of Model C TVs sold. D. Find the sum of the entries in row 1 of the matrix. What does this represent? So if we go to row 1 for our matrix, we've got these numbers. We have 206, 180, 150. If I add those numbers up, the sum is going to be equal to 536. So I'm going to write down 536. And then what does this represent? Because we are looking at row 1, we can see here at row 1, this is going to represent the number of sales for TVs at the La Mesa store. So I'm going to write down the number of TVs sold last month at the La Mesa store. E. Find the sum of the entries in column 2 of the matrix. What does this represent? So we're going to column 2. Column 2 here is going to be representing the Model B TVs. So if I add those up, I'm going to add up 180, 201, and 160, and that's going to give me a sum of 541. And what does this represent? This represents the total number of Model B TVs sold last month in all 3 stores combined. Section 2. Gauss-Jordan elimination with matrices. Matrices can be used to solve systems of equations. To do this, we will write an augmented matrix to represent the system, and then use elementary row operations to create a new matrix in reduced row echelon form. Elementary row operations, also known as row equivalent operations. 1. Interchange any 2 rows. 2. Multiply each entry in a row by the same non-zero constant. 3. Add a non-zero multiple of one row to another row. Example 2. Use augmented matrices to solve the system. We have 3 equations with 3 unknowns. We have the first equation, x minus y plus 2z equals 0. Second equation, x minus 2y plus 3z equals -1. Third equation, 2x minus 2y plus z equals -3. The first step is to make sure that all of your equations are written in standard form. That is, that they are written as ax plus by plus cz equals d. Once you make sure that all 3 equations are written in standard form, step 1 would be to write the augmented matrix. To write the augmented matrix, we are going to write the coefficients of the variable terms that are to the left of the equal signs, and we're also going to write the constant terms that are to the right of the equal signs. For row 1, we are going to have the following elements from left to right. 1, -1, 2, 0. And then for row 2, we're going to have 1, -2, 3, and -1. For row 3, we're going to have 2, -2, 1, -3. And notice that I'm going to draw a vertical line separating the coefficients of the variable terms from the constants. Step 2, perform elementary row operations to create a new matrix in the form, and here what you see is a 3x4 matrix that has in row 1, 1, 0, 0A, the second row, 0, 1, 0B, the third row, 0, 0, 1C. This is considered reduced row echelon form. So first what you see here is you're going to see my augmented matrix. In order to do row operations here, I'm going to have to determine how I can manipulate these rows in order to get ones, positive ones, going down the diagonal. and pretty much zeros everywhere else except to the right of my vertical line segment that I have here. In order to do this, the first row operation I'm going to do is I'm going to multiply row 1 by a -1 and then add it to row 2 in order to cancel out the first one that I have at the beginning of row 2. And I'm also going to multiply row 1 by -2 and add it to row 3 in order to cancel out that 2 that's at the beginning of row 3. So I'm going to show the steps here. Row 1 times -1 is going to give me -1, 1, -2, 0, and then I'm going to add it to row 2. And if I add those two rows together, I will end up with my new row 2, which will be 0, -1, 1, -1. So that's what I'm going to copy down now for row 2. For my next row operation here, I'm going to multiply by -2 to row 1. So I'm going to get -2, 2, -4, 0, and then I'm going to add it to row 3. Row 3 is 2, -2, 1, -3. And if I add those two rows together, I will get the following new row for row 3. 0, 0, -3, -3. Now I'm going to write my new matrix that I'm getting here after doing these row operations. In row 1, we are still going to have the same exact row 1, which is 1, -1, 2, 0. In row 2, we're going to have 0, -1, 1, -1. And in row 3, we're going to have 0, 0, -3, -3. Our next step here would be to try to get 1s going down the diagonal of our coefficient matrix. Our coefficient matrix is the matrix, or the part of the matrix that is to the left of that vertical line segment that I drew to separate the coefficients of the variable terms from the constants. So I see that in the diagonal of the coefficient matrix, I see a 1, a -1, and a -3. I can easily change that -1 that I've highlighted in yellow in the second row to a +1 if I multiply row 2 by -1. So that's the row operation I'm going to do for row 2. It's going to be -1 times row 2, and then that will produce my new row 2. And in row 3, I have 0, 0, -3, -3. So if I want to change that first -3 to a 1, I would need to either multiply by -1/3 or divide by -3. Either way is fine. I'm going to multiply by a -1/3. So I'm going to write down the row operation as -1/3 times row 3 is going to produce my new row 3. And I've highlighted that -3 in yellow so it stands out so you know which one I'm focusing on to determine which row operation I should do. So to the right of my matrix, I'm going to write down my row operations. I'm going to write -1 times r sub 2 is going to become my new r2, my new row 2. And I'm going to write -1/3 times r3 is going to turn into my new r3. I'm going to erase the work that I did below for the row operations that I did earlier. And I'm just going to go ahead and I'm just going to write my new matrix that I'm going to get after doing these row operations. So I'm going to go ahead and write my new matrix here. The first row is going to stay exactly the same. So I drew an arrow pointing to the right here. I opened up a square bracket to write my matrix. For row 1, from left to right, I have 1, -1, 2, 0. For row 2, we're going to have 0, 1, -1, 1. For row 3, 0, 0, 1, 1. And now I'm going to close my square bracket to enclose that matrix. Now if I look at my coefficient matrix, so that's basically the 3 by 3 matrix that I have farther to the left here where I don't include the constants. I do have a diagonal of 1s and I have 0s beneath that diagonal. So I'm almost there. I've almost achieved my goal. Now I need to create 0s above this diagonal of 1s. So I'm going to focus on I'm going to highlight the 1s in my diagonal so you can see that that's the goal I wanted to have. I did want to have 1s going down that coefficient matrix diagonal. But now If you notice the numbers that are above that 1 in row 3, I'm highlighting them in green this time. There's a -1 in row 2, and then there's a 2 in row 3. This is in column 3. I need those to become zeros. So I'm going to use my row 3. I'm going to multiply it. So I'm going to add a multiple of my row 3 to row 2 and row 1 in order to get those zeros. I'm going to multiply by -2 to row 3, and then I'm going to add it to row 1 to create my new row 1. I'm going to multiply by, well, I don't need to multiply by anything. I could just add row 3 to row 2 because they are opposites of each other, those coefficients, and I can just get 0 there. So I'm going to add row 3 to row 2, and that will become my new row 2. So let's go ahead and do that. I'm going to open up my square brackets here for my matrix. In row 1, we are going to have a new row. I am going to go ahead and show the work for this in the lower left-hand corner. So the first thing I'm going to do is I'm going to show -2 times r sub 3, or row 3. So I'm going to draw an arrow pointing to the right from this, and I'm going to write down the row 3 multiplied by that multiple of -2, 0, 0, -2, -2. Then I'm going to add this to row 1, so I'm going to write row 1 underneath, which is going to be 1, -1, 2, 0. If I add these two rows together, I'm going to end up with 1, -1, 0, -2, and this is going to represent my new row 1, or my new R1. So I'm going to write this 1, -1, 0, -2 for my new row 1. Now I've got to add row 3 and row 2. So R3 is 0, 0, 1, 1. R2 is 0, 1, -1, 1. And if I add those two together, I get 0, 1, 0, 2. So I'm going to write that down as my new R2, or my new row 2. 0, 1, 0, 2. And for row 3, I'm just going to copy it down exactly as it is. 0, 0, 1, 1. And I'm going to go ahead and close the square bracket, and I'm going to draw my little vertical line segment here separating the coefficient matrix from my constants. And I'm going to go ahead and erase all the work that I just showed down below. So all we're missing is one element here in row 1, column 2. I need to make that -1 in row 1, column 2 a 0. So I'm going to add row 2 plus row 1, and that's going to create my new row 1. So in the next part down here, I'm going to draw an arrow pointing to the right. I'm going to open up a square bracket for my matrix. And then further to the right, I'm going to show the work. I'm going to write R2 with an arrow pointing to the side to represent the row 2. That's 0, 1, 0, 2. R1 is going to be 1, -1, 0, -2. And if I add those two rows together, I get 1, 0, 0, 0. So that's what I'm going to write down for my new row 1. 1, 0, 0, 0. My row 2 is 0, 1, 0, 2. My row 3 is 0, 0, 1, 1. Now I'm going to close my square bracket, and I'm going to draw my little vertical line segment here separating my coefficient matrix from my constants. And now I'm going to erase the work that I just showed so that I can go ahead and write my solution. So this basically means x equals 0, y equals 2, and z is equal to 1. And when we write a solution for a system of equations, a system with 3 equations and 3 unknowns, we're going to do our step 3. We're going to write the solution as an ordered triplet, a, comma, b, comma, c. So I'm going to write this as 0, comma, 2, comma, 1. And I'm going to box that answer in, and that's going to be our final answer for this problem.